Hello, everyone, and welcome. We're going to wait another moment for more folks to join. And thank you for your patience while we wait for the participants to join the meeting, and we will start shortly. So hello, everyone. Thank you for joining. My name is Anna Herforth, and I'm the co-founder and coordinator of the Ag2Nut community of practice. Welcome back to the Ag2Nut members who have been part of this community for a long time, and also probably to new participants. Today, we are pleased to be hosting the discussion with the Periodic Table of Food Initiative on Foodomics, mapping the biomolecular diversity of our food. And we'll talk a little bit more about what that means, why we're having an Ag2Nut seminar about it, and the discussion that will follow. And you'll hear lots of rich content from the presenters today. Before we get started in the content, I see some people are using the chat. Please write into the chat feel free to write in the chat and include your location and the country where you're joining from. The webinar today will be recorded, and we'll be able to share the link to the recording as we do with other Ag2Nut webinars. And during the webinar today, you can use the Q&A function to write your questions for presenters. And we'll have a Q&A session that's moderated at the end of the presentations. So the first hour of today's session will be the presentations and the Q&A. And then after that, we'll have more time for discussion. So there will be another separate link that people who would like to stay on and have further questions to unmute and have a free discussion can do so after the webinar and the Q&A portion of today's event. And the Ag2Nut community of practice, we've been around for now 13 years, and you can join Ag2Nut if you have not already joined. I see a lot of familiar names in the chat. It's great to see everyone joining from many different places. If you're not a member of Ag2Nut, you can join easily at ag2nut.org. There's a very quick sign-up process, and what that will do is allow you to be part of the global network of now about 9,500 people in over 130 countries who share information and resources and things like job postings or event postings related to the linkage of agriculture and nutrition. And today, we're really happy to be hosting with Periodic Table of Food Initiative. We'll talk about this new initiative around Foodomics. What does that mean? Well, what's in the food that we eat? And how does what's in the food, including the nutritional content, the nutrient content, as well as the content of food related to other aspects that affect health, like phytochemicals, sort of what's maybe called the dark matter of food beyond nutrients, what actually is in food and how does it vary based on how and where food is grown, and what are the implications for people in terms of what production practices, what kinds of varieties will lead to different food composition that has effects on nutrition and health. So this topic really gets to the heart of the ag to nutrition connection in implications for production systems and the content of food. So you'll hear from several speakers here that you can see the topics and the names as well as the faces listed on this screen. And I will now turn over the presentation to our first speaker, Dr. Selena Ahmed, who is the director of the Periodic Table of Food Initiative.
Thank you so much, Anna, for the introduction, and thank you for all of the participants for joining us today. I am delighted to share about our efforts with the Periodic Table of Food Initiative, as well as our integrative approaches for Foodomics. We are going to start off with a trivia question. Food, as we'll hear about today, has a diverse range of components. One of those many components that are recognized for their health attributes is a phytochemical or a specialized metabolite known as epicatechin, something that I value being a researcher who's long looked at tea. This is a bioavailable component found in tea. Where I live in Bozeman, Montana, I wanted to know what local foods that are actually in my own home garden contain this phytochemical. So you can put it in your chat window if you think the highest concentration or relative abundance of epicatechin was found in A, basil, B, plum, C, green pepper, or D, tomato. Looking at data, initial data on 100 fruits and vegetables generated by the Periodic Table of Food Initiative on some of the phytochemicals in fruits and vegetables, we see that epicatechin is found in multiple foods, including apples, plums, and raspberry, with the highest relative abundance in plums. But you can also say, well, what type of plum? We know that not all plums are the same, and also the different cultivars have different variation of their food composition. So the next trivia question is, how many varieties of plum are there? A, 12, B, 50 to 100, C, about 600, or D, 6,000? You can put in the chat window your knowledge or thoughts or guesses about that. Well, the scientific literature indicates that there are 6,000 cultivars of plum from 20 to 40 different species. So really a tremendous diversity of plums that all vary in their composition. Often when we think about food composition, we think about it as static, but in fact, it is variable across the food system. Today, we'll be hearing from Jonathan Lundgren on how different regenerative or different agricultural practices, including regenerative agriculture, can impact the composition of produce and grains. And so, for example, plum, the scientific literature already indicates the composition can vary based on multiple growing practices, including climate variables. And then as that plum travels across the food system, the composition can further vary. So this might be if that plum is processed into a preserve, if it's dried, or if it's pickled. Storage and distribution and food procurement may further impact the quality or composition of that plum, including storage conditions, humidity, and then ultimately how we choose to consume that plum, whether we're eating it fresh or we're deciding to ferment it, put it in a stew, or bake it into a cake. And so lots of variation happening with that composition as it travels across the food system. And so this example of the plum is just one to illustrate that our food systems are diverse and dynamic. The planet has incredible edible biodiversity that reflects ecosystems and cultures. At the Periodic Table of Food Initiative, we really are trying to celebrate that diversity of foods, including the diversity at the biomolecular level. And so whether our diets look like this is a diversity of wild foods and ancient crop varieties at a table in an Aka community in the uplands of Yunnan province in China. Or our diets look like this: plant-based planetary health plates. These are recipes designed by Chef Alejandra Schrader. How well do we know our food? How well do we know the components of our diets? And can better knowing our food enable us to leverage food systems to deliver healthy food for both people and the planet? There are diverse ways of knowing food. Some of these ways are rooted in land-based and cultural practices, traditional ecological knowledge, and social exchange, such as this management picture of an agroforest. Other ways of knowing food, such as Foodomics, which is the topic of this webinar, leverage technological innovations to characterize the diverse known and unknown components in food towards identifying their role in health, nutrition, as well as ecosystem functioning. Tremendous progress has occurred in our ability to characterize food components since the landmark USDA publication in 1894 on the nutritive value of foods. Specifically, characterizing food has evolved from consideration of food as energy sources to understanding the role of essential nutrients for public health, very much enabled by the development of standardized methodologies. This includes the macronutrients, proteins, fats, carbohydrates, micronutrients, vitamins, and minerals, and increasingly specialized metabolites or secondary metabolites or phytochemicals, including flavonoids, terpenoids such as the carotenoids, as well as alkaloids. In addition to these endogenous biomolecules, there's also components that enter a food and through food system practices, including processing and agricultural practices, both natural and synthetic components that can have both beneficial and deleterious impacts on human health. And so the specialized metabolites are increasingly being measured because they're recognized for their potential role in promoting health and preventing disease. We spoke about epicatechin in plum, but in addition to epicatechin, we also see there's a diverse range of other flavonoids and other components in plum that give it its attributes for human health, very much highlighting the importance of consuming whole foods and thinking about diverse diets. And then in addition to the known components in food, discovery data also indicates that there are thousands of unknown components in food. This is the dark matter yet to be explored. And so this is what the Periodic Table of Food Initiative is trying to do, to provide standardized tools to really profile all of the components of the planet's edible biodiversity, make this data from these tools accessible in an open access data platform, and then provide training through our educational platform, which we'll be hearing about today, Food EDU, to really see how we can translate this data to drive evidence-based solutions across the food system. And the Periodic Table of Food Initiative is managed by the American Heart Association, where I am based, as well as the Alliance of Biodiversity in SEAT. I wanted to emphasize that the standardized tools that the Periodic Table of Food Initiative is developing are to complement existing food composition methodologies where standardization exists, such as that used by many national food composition databases around the world. And so we can view this in 3 tiers. There's tier 1, where there's existing standardized tools, such as for crude fat or total starch, specific vitamins, quantification of these vitamins, where existing standardized tools exist. We haven't innovated, and we're utilizing these tools to populate our database. Then there's tier 2, which includes specific measures of macronutrients and micronutrients, where existing standardized tools do exist, but where the PTFI saw some room for capacity strengthening, such as reducing the cost of analysis through innovation of standardized tools. An example are specific minerals and metals. Then there's a tier 3, and this is really where we're expanding the frontiers of standardization for understanding our food. This is where tools existed, but that were not standardized and not distributable. And the bulk of these really are thinking about the metabolites, the phytochemicals that I spoke about, as well as several classes of macronutrients, including specific lipids, as well as dietary fibers. So this is where a bulk of our innovation has focused, and which my colleague, Steve Watkins, will do a deeper dive on right after my talk. Key to our effort of understanding food composition is understanding the rich food system characteristics that shape food composition. So very much we're working on developing guidelines to capture this variation across the food system, whether with shifts of agriculture, the environment, as well as cultural attributes. As a capacity enabling platform, we are developing an ecosystem of partners around the world where we're onboarding the democratized tools that we're creating to enable partners to profile their local edible biodiversity, as well as answer research questions that are locally relevant. We have centers of excellence on each continent. We are also working to build a national lab hub around the world. The goal is to work with one national lab in each country, as well as research partners beyond that. And so as I conclude, I wanted to leave you with one question. By better knowing the components in food, can we better define healthy diets? Can we better have more precise agricultural guidelines, as well as other guidance in the food system, so we can really make those agriculture to nutrition linkages? I support that Foodomics, applied in a holistic way to complement other forms of knowing food and diets, can inform evidence-based decisions and solutions in unprecedented ways. I am now going to pass it to my colleague, Steve Watkins, who is the lead strategist and technical advisor for the Periodic Table of Food Initiative, and also a founder of Versa Biosciences. Over to you, Steve.
Thank you, Selena. I am going to pick up on a topic that Selena started about the technology that we're developing for the PTFI and how we think about how it fits together with existing tools and complements them and builds out our understanding of food composition in its entirety. And I think there's a data visualization that kind of represents the framework that we think about. If you think about foods, I'm a food scientist by training. We learn about proximate analysis. We think foods are water, protein, carbohydrate, lipid, and minerals, and ash. This is proximate analysis. This is the foundation of a lot of analysis of foods. Really kind of the basic components bucketed into general macronutrients. But I think as we learned more about nutrition, as we start to be able to convey what's important about foods to people, what they need to eat to be healthy, we learned that things like the amino acid composition of that protein is important, or the fatty acid composition of the oil is important. And that's really represented here in the second ring, where we have a lot of terrific tools for working through the nutrient components of food. But where we begin to look at innovating technology is really diving a little deeper here still. So if we look at just carbohydrates, you can break carbohydrates into fibers, sugars, starches, and each of those components has a chemical composition that's unique to the food and is important for our ability to either digest that material or important to which microorganisms in our gut can ferment it. And so you can break these fibers into the different sugar types, and those sugar types are linked together in different ways, and we can measure the ways in which those different sugars are linked together. And the same is true for lipids, where we can break things out into oils and membrane materials. We can take a look at the oils themselves and look at what fatty acids comprise those oils, and really start to understand something much deeper about not only the nutritional composition of foods, but also the biochemistry that goes into producing all of these chemical components. So give us a deeper understanding of how we could manipulate food through agricultural practices, through food processing, et cetera. So that's how we think about it. When we started the project, we sort of hit maybe an obvious wall for those of you who've been in the omics space, but we sent 10 foods in blinded duplicate to about 15 labs around the world who are experts in small molecule, what they call metabolomics, or lipid analysis, lipidomics, or mineral analysis, ionomics, glycomics for carbohydrates. And we asked them to do the best job they could at measuring what was in those foods and to report back to us what was in them. And what we got back was each lab was very good at saying that the same components were present in the duplicates we sent. So we'd get very comprehensive lists of compounds that a lab found in a food, and those matched between the blinded duplicates we sent. But when we compared different labs, we got almost no overlap in terms of the chemicals that had been reported in those foods at all. And so the ability to annotate and name compounds in foods beyond the standard nutrients was really in chaos. And it needed some standardization and organization. So that's what we focused on. We focus on standardizing the analytical platforms that are used to make these measurements. And we did it in 4 ways. One, we looked for protocols that were already in use and had been robust and shown to work over time with foods. But we manufactured a set of reagents, chemical compounds in mixes, that we ship to every lab that participates in the PTFI network of labs. Those reagents include internal standards and standardizing components, as well as reference materials that are run with every batch to ensure that the data that a lab is generating are consistent. And then internally, we worked to collect a series of physical compounds, chemicals that we know are in food, to run through these systems so that we could really understand what signals they provide on our standardized platforms, so that when we see them in any lab in the future, we are confident in annotating that value back to the original compound. And then we developed a lot of open centralized data pipelines, some of which you'll see from Qiming later, that that are linked to these reagents and these reference materials that support our lab network in the processing of the data. So our labs can just bring the data back to these central data pipelines, and the data pipelines process all of the results in a consistent way and return the data to the labs. So we've done this across a variety of platforms. As I mentioned, metabolomics for small molecules and bioactive components, lipidomics for complex lipids, glycomics for carbohydrates, ionomics for minerals, and we are in process of developing more standardized approaches to proteomics and aromatics or volatile compounds, the things we perceive as flavors and aromas in foods. So just a quick note on standardization. This is sort of what it looks like when you can standardize labs across geographies. So the dots on the plot on the left are actually the post-time normalized values for all of the internal standards that we provide to the labs. And you can see that after we run our alignment data processing routines on them, the 30 or so compounds that are present in each food are highly aligned between labs. And this is across, again, those 10 foods measured in duplicate. So now we have aligned the signals that are coming out of every lab, and that allows us then to build this library of understanding by running chemicals in multiple places, making sure that they come out at the same time with the same mass and the same signal. We build this consensus across labs of what it means to see a certain compound on these platforms, and that's shown in the figure on the right. So all that said, that's sort of the underlying technology. This is where the fun starts. This is the first 100 foods that we processed for the PTFI, and it's looking at our, well, maybe some of our favorite compounds in foods. These are polyphenolics. So it's 100 polyphenolics that we looked at across these foods. And on the right, you can see the foods, and you can hover over a food and see which specific compounds that food is enriched in, right? On the left, cranberries have a lot of compounds in them. Apples have a lot of compounds in them. Or you can look at your favorite compounds. You can look at narogenin and see that it's present in the citrus components. You can look at limonene. Oh, it's also in the citrus components, or genistein, which distributes across the legumes. But in this way, we can start to really understand at scale across all of these compounds, where can we find these compounds in the food supply? How do we know which particular components of our food systems are rich in these bioactive important metabolites? So, okay, so that's for things where we can, buy a compound and we know what the signal looks like, and we can document for sure what we're looking at. But what about what people call the dark matter of food? So the dark matter is all of the other compounds that we don't know what they are yet. And I'll show you in a minute. This is a pretty vast space. It's a little daunting, actually. But one thing we can do is take advantage of the standardization we've built across these platforms to collect a lot of information about every signal that comes off of the mass spectrometers in a very standardized way. And that signal includes the time it takes for that compound to come off the platform, which is related to the polarity, the formula, the chemical formula of the compound that's coming off the platform. And then we do two other things. We do what's called MSMS, the tandem mass spectrometry, where we fragment the molecules and we look at the pattern by which they break, which is indicative of what kind of molecule it is. And we also run all of the reference foods or the inspirational foods we're running through a process called ion mobility spectroscopy, which for every signal we see in the study, it basically gives us a shape of the molecule. So we can tell isomeric compounds apart. Where do we see L isomers? Where do we see R isomers in food? And all of this information is tied back to the standardized values that we're collecting in the database. So we have, even if we don't know what things are, we are building a standard catalog of the food that we measure. And this is one of the early examples of where we tied all of that information together around some foods. This was 10 foods where we collected all that. And you can see on the left, it was 2 lentils, a brown lentil variety, a red lentil, corn, 2 strawberry varieties of 2 strawberries each in conventional and organic, some carrots, wheat flour, steel cut oats. And we took the top 1,000 compounds we saw in this study. And what you see in red is where those compounds are highly abundant in the food, and blue means they basically didn't exist in those foods. And the x-axis here is a series of slices of these 1,000 compounds. And I think the thing that jumped out at me and is both exciting and daunting is that the diversity and abundance of these biochemicals in foods is huge. In plants especially, most plants have a mostly unique composition to them. So the vast majority of compounds in a plant are unique to that plant or food type or plant type. And that we have a lot of work to do to be able to name all these compounds. However, that's what we're doing. And we're building this complete catalog. And I note that even though if you look here, strawberries, the conventional and organically grown strawberries look very similar, the data itself speaks to a separation of sort of phenotypes of these foods. In this case, conventionally grown strawberries versus organically grown strawberries. The data do separate these things. And now we can begin to look for specifically what components in these strawberries differ between these 2 interventions. So even if we don't know what things are yet, we can use these tools to start to describe differences and start the work of really building understanding around some of these critical questions of human and planetary health. And with that, I'd like to stop sharing and introduce Jonathan Lundgren with the Ag2Nut Foundation, who will talk a little bit about the use of these tools and some of the work that he's doing.
All right, thanks, Steve. So I'm John. I run Ag2Nut Foundation and Blue Dasher Farm. We're based in South Dakota, and we're trying to bring science to the field of regenerative agriculture. Why on earth would we be talking about production agriculture at a nutrition conference, right? Well, the nutrition of the foods that we eat on a daily basis is inextricably tied to the soil and the way that that food was produced. And regenerative agriculture is making some pretty bold claims that data is now substantiating to some degree on just how well we can produce that food in order to sustain our planet as well as our own nutrition. What is this thing called regenerative agriculture? You know, I think at its basis level, what regen ag does is it connects humans back with nature, family, and community. And it does that in practical ways, okay? And what we have found is that across farms around the globe, that these practices end up fitting into different buckets. These universal principles, okay? So first off, these farms that are regenerative often and usually stop tilling. They stop soil disturbance. And then they cover that soil. They cover it with plants, all right? And those plants, the more diversity in that plant community, the better. This is another principle that we tend to see. And then we're not going to solve a lot of these planetary scale problems unless we start integrating livestock back into our food system and managing it appropriately. And what we found is that as farmers have adopted these systems, they don't need to use a lot of the synthetic chemistries that used to support the productivity of their farms. And so eliminating synthetic chemical use tends to be one of these principles. I was talking with one of the conventional farmers that we were working with out in California, almonds. He was an almond producer. And I showed him the data from his farm, and he said, he looked at it, he's like, I don't believe it. I do not believe it. I did everything that I was supposed to do. I followed the best management practices of the universities, the almond board, and I sprayed insecticides 5 times last year. It cost me tens of thousands of dollars. And what you're telling me is that the folks right across the road from me didn't spray insecticides at all, and they had the same pests that I had. And I can't believe that. That's where science becomes so important. Okay. That's why science is so important, to take anecdotes, these success stories, and translate them to the greater population. Okay. Give us some predictability. We explained to that farmer that it wasn't just the neighbor across the road. It was all of those regenerative farms in a replicated fashion. Okay. That farmer took that data and our relationship with him, and he changed 1,000 acres of almonds over to regenerative production. Okay. Science and data are so desperately needed right now. But we have to, as scientists, understand that the data is not sufficient in order to change behavior. That we have a real mistrust of science. We're saturated as a society with information right now. How do you know who to trust? And scientists need to understand that these relationships and trust are so inherent in behavioral change and adoption and making that data stick. Enter in the 1,000 Farms Initiative. So Ag2Nut Foundation is working on a continental scale, trying to provide some scientific robustness to the claims that regenerative ag seems to be making. Does regen ag work no matter what you grow, where you grow it? And farmers are developing successful regenerative systems. How are they getting there? Can we empirically tease out different processes and practices that seem to expedite the adoption and the outcomes of a regenerative system? So this is where we were over the last 2 years. You can see we're operating at a pretty big scale, and we're shooting out from that little green star right in the middle of nowhere, South Dakota, and ground zero where change needs to happen. Still plenty of areas of North America that we still need to touch, but we've been on 737 farms so far as part of this study. So lots of data. On each of these farms, we're measuring as much of the system as we possibly can. We're collecting forage samples, we're collecting yield samples from each of these farms, and we're looking at nutrient abundance and diversity from those farms. Okay, that's really important, and we'll be discussing 3 of those focal systems that PTFI has been working with us on. We're looking at soil carbon, soil chemistry, soil physical properties, reversing desertification of these farms, and then biodiversity, life on these farms. Really, really important, okay, in all of its different facets. And then finally, we're looking at the socioeconomics of these different farms. And we're knitting all of this systems level data and supporting how many things that nutrition of these food products ends up being driven by or working with on these farms. What are we finding? This is on a national scale. Oh, let's put that back. On a national scale, we're seeing that the number of regenerative practices, as farms start to adopt more and more of these positive practices, that things like soil carbon and organic matter and productivity of these farms ends up increasing substantially. Okay. In 5-10 years, based on the results of this work, in 5-10 years, we won't even be talking about things like soil carbon anymore. Okay, we'll be talking about life. And our projects are actually developing entirely new technologies in order to be able to measure this life and empower farmers to measure the life on their own farms. As you might expect, the more regenerative practices that a farm uses, life responds to very positively. Why is life so important? Because that is the mechanism whereby we end up seeing a lot of these regenerative outcomes realized. Okay, the life sequesters carbon. It reverses desertification. It allows that soil to hold on to water. It's biodiversity, right? In all of its facets. We're excited to be globalizing these efforts. Taking what we're learning in North America and transmitting it onto a global stage is very exciting for us as we're moving forward in the next few years. And I would like to thank many, many, many people, and looking forward to that even more and more. And next will be Chi Ming, and he'll be talking about some of the data that we've been working on together.
Hi there. So thanks a lot, Jonathan. The work that you're doing is so exciting and so important. My name is Chi Ming Chen with Verso Biosciences, and I lead the PTFI's data workstream. And I wanted to dive a little bit deeper into some of the data, and I'm going to first orient you into what PTFI is collecting about food generally, and then I'll drill down into some of what we can observe in Jonathan's data. So what you see on screen is the Marker Lab interface for the PTFI database. And this is an interface that's been developed for a research audience. It's configured with visualizations and groupings and comparisons that we expect to be valid. So as an example, we're going to start with some data that we have on broccoli. All of our food is organized ontologically. So broccoli is a cruciferous plant in the Brassica family. And by organizing it ontologically, this allows us to aggregate information about food's composition into meaningful groupings, like the abundance of a certain compound in plants or in Brassica. And in addition to the broad set of compounds, broader than most food composition databases that we're gathering, we're also collecting standardized metadata. So here, I'm going to show a particular sample of broccoli, and you can see information about what that sample was. So broccoli floret in this case, what cultivar of broccoli this was, what the production system that broccoli was produced in, and even geolocation data. In this case, this was a field collection. And so we have information about the field where this broccoli sample was collected. With this information, this could allow a researcher to connect to external databases like precipitation levels, historical. And this metadata also really begins to allow us to ask and to answer some of the really big questions, like the effects of our methods of production on the quality of food, and also how climate change might be affecting the quality of our food. So we've started with a core set of metadata, but the system really has been designed to be extensible. And with that, let's take a look at Jonathan's experiment in particular. So we'll look for the Ag2Nut 1000 farms data. We currently have data from Jonathan from 3 different foods: apple, wheat, and almonds. And what we've done is we've grouped these samples into 3 groups that summarize the level of regenerative practice on a particular farm or production site. So low, medium, and then highly regenerative. If we take a look at some of the compounds that we've measured within the highly regenerative almond group, we have this view, a z-score report. So a z-score is a measure of how different a value is compared with the average value in a population. So specifically, how many standard deviations we are at, or we are above or below the mean. Over here on the left, we can control that what we're comparing the highly regenerative almond samples to. And in this case, it makes sense to compare it with all of the almond samples in the Ag2Nut experiment. In the center panel, this shows individual compounds that we've measured in our high almonds group. And I'll point out that there are some compounds here that are identified by chemical formula only. So as Steve has mentioned, we're cataloging the dark matter of food. So even if we can't name a particular compound, we know enough to record a unique signature for it. And that's what you see here. To help us make sense of what we're seeing, we can turn on our sets. These particular sets are organized biochemically, but they are configurable so that if we want to see a view geared towards nutrition, we could easily configure new sets. If we focus in over here on the specific classes of lipids that we've measured, we see that almonds rated regen score high have higher than average total triacylglycerols and lower free fatty acids. So this might indicate that there's less breakdown of these particular lipids in the highly regenerative context. And this seems like it's something that could be worth additional exploration and follow-up. And we can also drill down to see the distribution across samples. So I'll note that existing food composition databases generally don't capture this kind of breakdown into specific lipid classes, and that some of these lipid classes, the MGDG, SQDG, and DGDG, these are plant-specific lipid classes that are being profiled for the very first time using PTFI methods. Next, if we turn our attention to minerals, we also see that in the highly regenerative context, several toxic heavy metals appear to be lower in abundance in the highly regenerative context. So arsenic and lead and cadmium. And I'm going to close out by looking at some of those a little bit more closely. So I'm going to start with searching for lead. Here, we are looking at lead in each of the almond samples, organized by the level of the farmer's regenerative practice. I'm going to adjust the view a little bit so that we can have an easier time seeing the overall picture. We see that the regen score low experimental group has actually more samples that have more lead relative to the overall set. And then the almonds that were grown in a highly regenerative context have fewer lead samples, or fewer samples that are high lead, and that those samples generally have a lower amount of lead. And if we adjust the scale factor over here, we can kind of get a better picture of comparatively what that looks like. Taking just one last example, cadmium, another toxic heavy metal. In this case, you see that, again, the low experimental group actually has more samples that have greater cadmium content. And the medium and high also appear to have, each have several samples that are higher than average. But we can tell from the sample identifiers, and we can actually see if we were to drill down to look at a particular sample and their metadata, that the 4 samples in the highly regenerative group that are high in cadmium are actually all from a single site. So the level of regenerative practice doesn't completely characterize the difference here, but this might be motivation to drill down into site-specific conditions, which we could further explore because we have that location metadata. So with that teaser into the types of data that we'll have at our fingertips, I'd like to introduce Dr. Gina Kennedy, PTFI's Director of Research and Translation, to discuss research questions that PTFI data and research projects aim to address. Gina?
Thank you, Chi-Ming. That was just absolutely fascinating. And I've been looking at everybody put their names and affiliations in the chat. We have this beautiful global group. It's so exciting. Thank you for joining this webinar. I am Gina Kennedy, the Director of Research, Translation, and Impact at the Periodic Table of Foods Initiative, and also a Principal Scientist with the Alliance of Biodiversity and CIOT. So it's my great pleasure to talk to you today, give you a very brief introduction to some of the research opportunities that the Periodic Table of Food Initiative will be bringing your way very soon. So the Periodic Table of Food Initiative is a database that we want to use to explore pressing food system challenges. We read every day in the paper and we hear every day on the news about these pressing challenges. We would like for the Periodic Table of Foods Initiative to be able to help us better understand the relationships between climate change and food quality, agroecology and regenerative agriculture practices and food quality, and the linkages between agriculture and food quality and health. We have some very large overarching questions that we're hoping to be able to answer. How can we grow food in ways that are good for both people and planet? And can we produce food that is more nutrient dense, desirable, affordable, and uses fewer resources? In terms of looking at climate change, we really do want to understand how do environmental factors impact food biomolecular composition, and how does this impact our food quality and our nutrient supply? going way beyond what we know about protein and a handful of micronutrients and the effect of climate change. In terms of agricultural practices, I think Jonathan's example and Qiming's data from Ag2Nut Foundation are very illustrative of these research questions. How do agricultural practices impact food quality and nutrient supply? How can we adapt growing practices to improve human and planetary health? And finally, the relationship between food composition, health, and nutrition. We're looking to better understand how different types of biomolecules influence human health. Which specific biomolecules in our food contribute or detract from our health, and which production practices are linked to abundance or lack of protective or detrimental biomolecules in our food systems. So how are we going to do this? Qiming already showed you our standard food item data. We refer to this as metadata. And we're being very intentional about linking these domains of agriculture, the environment, agricultural practices in how we're collecting and how we're creating the database. So we're also being very intentional about the provenance of food. Selena talked about over 6,000 cultivars of plum. We want to know the location where the food was grown or sourced, the variety, cultivar, or breed of the food, and maybe the center of origin where this came from originally and then has spread about the world or is still more localized. And we want this to allow users to explore more deeply the differences in bioactive molecules within these varieties, cultivars, and breeds, but also even understand how food composition within the same species and perhaps variety may vary by geographic location in which it was grown. As the database continues to grow, we want to include social, cultural, and economic data also on the food and really tie this into our food traditions and our ways of knowing food. So how are we going to populate the database? We have a global network that Selena showed that consists of centers of excellence, demonstration projects, and national labs. And here's just a small selection of some of our demonstration projects that are run by our centers of excellence, as well as our partners such as Jonathan at the Ag2Nut Foundation. I'm going to just dive deeply into two of these as examples. So the National Institute of Nutrition and Medical Sciences in Mexico has a project that is going to map the metabolome of commonly consumed Mexican foods. You can see that they've already prioritized their foods, including corn, amaranth, avocado, nopal, guava. And they also want to look at the bioavailability of the metabolites and the biomarkers of intake of these highly consumed foods. They already have prioritized some compounds of interest, including fumonsin in corn, novel fatty acids in amaranth, and the many bioactive compounds that we already know are in cactus or nopal, and that have biologically relevant activities, including anti-inflammatory, antioxidant, hypoglycemic, antimicrobial, or neuroprotective properties. Another example of a demonstration project comes from two of our other centers of excellence across the world in Ethiopia and Ghana. In this project, they are going to investigate soil quality, food composition, and human health linkages. They hope to answer questions such as, what is the state of soil health in Ethiopia and Ghana? What is the impact of soil quality on food composition? What's the level of dietary exposure to chemical hazards? What is the effect of consumption of crops grown on soil of different quality on serum inflammatory biomarkers? So those are just a few examples of the database that we are building with this amazing set of a global team, building a necessary new database for people and planet. One of our scientific advisors, Bruce German, said it, I think, just beautifully. It will be a database that captures and quantifies the molecular content of food and will revolutionize the agriculture, food, and health sectors. Once in place, this publicly accessible database will be the greatest single knowledge asset in the history of food. So thank you for joining the webinar, and thank you for wanting to be a part and learn more about this global team that we're building, and we hope that you will join us on this journey. I'm now going to pass over to Kevin Cody, who will talk about our capacity strengthening programs, Food EDU, and Good Food Fellows. The floor is yours, Kevin.
Thank you. Thank you, Gina. And thank you everyone for being here and for this opportunity to present Food EDU, Education to Nourish People and Planet. All the presentations you've seen today are in effect becoming educational modules for a global audience in Food EDU's course track, Foodomics and Society, which I'll talk to you a little bit more about today, as well as some of the other opportunities that we're developing with Food EDU. Oops. Our mission is really bridging gaps and building capacity. We were seated as a capacity strengthening initiative of the Periodic Table of Food Initiative that recognized there was this gap between the innovative research taking place in regards to foodomics, food composition data, and the educational opportunities for a global audience, such that that audience could apply the findings, contribute to the database, and advance human and planetary health with the research that's coming out of the Periodic Table of Food Initiative. We're also attempting to bridge geographies and disciplines with Food EDU, such that learners across the world and from various sectors can have a language with which to speak to one another about the importance of food composition data for everything from public policy to things like agricultural practices, and nutrition and dietitians alike could be able to speak to one another about how food composition data understood in this way could really advance human and planetary health. We are managed as a co-secretariat with the American Heart Association and the Alliance of Biodiversity, CIAT, and again, with the Periodic Table of Food Initiative being a really critical partner in this work. This is just an example of some of the core offerings for Food EDU. We'll be developing a number of different online courses, again, with an interdisciplinary lens, focused on issues like food quality and many of the topics that came up in our presentation today. We're also developing a fellowship program, and we're pleased to announce that we've just awarded 6 of our centers of excellence funds to create the first inaugural cohort of Good Food Fellows, which I'll talk to you more about momentarily. We'll also be developing a series of trainings and workshops such that individuals around the world could take some of the work that we're developing here and bring it into their own institutions and teach some of their own stakeholders the kind of material that we think is going to really help advance this field. Lastly, we're developing a networking platform that will provide a dynamic and interactive engagement opportunity for learners across the globe to share insights and ideas, collaborate on research, and perhaps pursue collaborative funding opportunities as well. The first course track that we're developing for Food EDU is called Foodomics and Society. This is a course that will be introducing interdisciplinary concepts and guiding principles to frame the study and application of foodomics. As we learned in these presentations today, this is a really complex topic, and our goal is to really use the evidence base to drive innovative solutions and applications of the data that can advance human and planetary health. But we're also interested in addressing some of these fundamental questions about what are the most pressing challenges that we could address using this data and using these tools. Who is the research in service to? Who benefits? In that way, we'll be focused on issues of access and equity. How can we use foodomics to drive systems change, orienting the science to addressing these food systems challenges? And lastly, how do we work across disciplines and geographies to achieve these common goals? Again, with the goal of building some fundamental literacy across different sectors and domains to enable some of these conversations that could really enhance some of the goals that we're striving to achieve. One of the other things that we're doing at Food EDU is establishing a Good Food Fellows Fellowship program. As I mentioned, we recently funded 6 of our centers of excellence that are in Mexico, Colombia, Ghana, Ethiopia, Fiji, and Thailand, who will be funding the inaugural cohort of Good Food Fellows. These fellows will be doing community engaged research to apply and utilize and contribute to the database that PTFI is developing, really providing a foundation for future research as well, using the tools and data to help us that are helping us understand food in these new and innovative ways. The Good Food Fellows will also participate in some professional development trainings to support their work, thinking about access and benefit sharing, science communication for a diverse audience. And again, we'll be using the engagement hub as an opportunity to allow fellows to connect with one another and to develop a broader community of practice around this work. This is just a small taste of what Food EDU has to offer. Some of our initial course modules will be available this spring. They will be completely online and open access. But we'll also have our inaugural webinar in November, and I'll share with you the dates here, titled Connecting Food Quality to Human and Planetary Health. This webinar will be on November 15th at 10 a.m. and 6 p.m. Eastern times. And the goal of which is to help our participants learn how diverse ways of knowing and measuring food quality can promote sustainable food system sustainability and improve human health. And I'll put some registration links in the chat. And thank you for your attention. I'm going to turn it over now to Tracy Shafizada, PTFI lead strategist for technology partnerships, will lead our Q&A session. To you, Tracy.
Thank you, Kevin, and thank you to all of our speakers. I hope everyone has enjoyed hearing a little bit more about our long-term vision at the PTFI, which is to create a publicly available database of deep compositional knowledge of the global food supply. And the pillars that support this vision really are around tools, data, and training. So you've heard a little bit about the analytical capabilities we're building that will augment existing methods that are used today for essential nutrients. You've also heard from some of our partners and demonstration projects, such as the work done by the Ag2Nut Foundation, who are really using and applying the PTFI tools and data to answer questions around regenerative agriculture and the effect on food quality and composition. You've also heard a little bit more about the different centers of excellence we have around the globe who are also applying the PTFI technology, data, training, and tools to answer their important research questions. And finally, you've heard a little bit about Food EDU and the educational models that will be available to build capacity around the world around food composition, quality, and foodomics. I want to remind everyone that the PTFI will be launched publicly in April, and you'll be able to mine the data. You'll be able to access the protocols and methods to participate in running these analytical platforms in your own labs, or submit your samples to labs who are serving as core service providers for the PTFI. You'll also be able to access the educational modules in April. So please stay tuned. We've reached the point in our webinar where we are now open for questions. I will remind the audience to please submit your questions through the Q&A tab at the bottom of your screen rather than the chat tab. And the first question that I see is, would there be harmonized guidelines and analytical tools that would be available across the globe, like for macronutrients and micronutrients in conventional food composition? So I'm actually going to pass that to Steve Watkins, who will be able to talk about the standardized and harmonized guidelines and methods that we are using for the analytical tools. And then we may actually pass it over to Sarah to talk about the protocols for sample collection. Steve.
So the short answer is yes, there will be publicly available protocols for running all of our platforms and publicly available reagents for doing the standardization. We are in the process of beginning to put those in a public-facing portal, and we'll continue to build out that resource as we learn things about specific foods that need specific handling. We hope the community will contribute all of that knowledge so that we can collect it in one place and make sure that everyone has access to the standard protocols and guidelines for generating the data. Sarah?
Yeah, thanks, Steve. So just speaking to the metadata and sample collection aspect of that both Selena Chi-Ming and Gina all mentioned, we are definitely standardizing not only the analytical applications, but exactly how we are procuring, collecting the foods, all of the metadata we're associating with that collection. And so if your question is about agricultural practice, detailing all of the agricultural practices of a given food, and then further standardizing how we're processing on the benchtop. So that's what we call intake processing. And then on down the line with standardization. So basically we're able to standardize every aspect. So our data are highly comparable and highly harmonized, as you pointed out. Over to you, Tracy.
Great. Thank you both. Our next question is asking, will there be further information on the impact of diverse food processing in this initiative? So I'm going to pass the question to Selena to talk about the types of foods and the types of metadata that we are collecting that will be available in the PTFI database come April. Selena.
Absolutely. So the first set of foods that we are analyzing in the initiative are inspirational foods that were nominated by partners around the world. Those are mostly whole foods that are unprocessed or minimally processed, like cheese. However, the tools can be applied to look at a range of food types as well as their processing. So we have started to look at some cooked and prepared meals as well. So not just what's in an apple or in a plum, but in an entire plate in front of us. And so ultimately, we'll also be able to utilize the tools to look at ultra-processed foods. Many of our demonstration project partners are very interested to look at the impacts of processing on food composition. For example, we have a demonstration project really interested in looking at the impacts of fermentation on food processing, how various microorganisms impact the ultimate food composition and quality, how the duration of fermentation and the conditions of fermentation impact food composition. So that metadata that Sarah is really leading the structure of is going to enable partners that access the database to be able to then see how these variables drive variation in food quality.
Great, thanks, Selena. The next question I see is, how do you decide which compounds are important to measure in a specific food sample? The person is asking this because there are numerous compounds and measuring all of them for every food type may not be cost efficient or effective. That's a great question. I think several of us on this call will have pieces of the answer to this. I'm going to start with Steve and then have him pass to others who may have some ideas on what classes, what compounds, and what approaches we can take to making sure we're measuring everything in a food. Steve.
It is a great question. There's a lot of things that can be measured in food, and they have a lot of different applications for different types of research, health applications, et cetera. So, but the answer is a little bit different for different applications for different platforms. So obviously what we talked about today was sort of our global platform where we're trying to build this catalog of everything that we can in foods. But in parallel, we are developing what we call targeted panels. So where we use these same approaches and same standardizing tools with a smaller set of compounds being measured with increasing efficiency, accuracy, et cetera, when we target them. And for those, some things we know are important, fatty acids, minerals, and we've actually done the work to build targeted panels for things that are obvious, that are already important. there are other areas where we look to you and we look to our centers of excellence and other places around the world to define what needs to be in a targeted panel, or to propose platforms that we can adopt and standardize with our tools on behalf of the overall effort. So I think it's a conversation with you and with others, but we are developing approaches at both levels of this global catalog and then these very sort of efficient, targeted, highly accurate panels. And I'm looking for hands to hand it off to next.
I'm just going to jump in. I also think it's a great question because the approach we're taking right now is not cost effective. We are putting a big investment into mapping everything that we can know about what is in food. And then we hope that this data of understanding these diverse food components can then enable us to move to the next step to really start to answer what in food is important to measure. Also, when we talk about these different methodologies or tools, when we're talking about fatty acids, there's one tool. When we're talking about the phytochemicals or specialized metabolites, there's one tool. And so different labs around the world who are interested in onboarding or utilizing these tools may choose one specific protocol or tool for your research question. So you might, I'm really interested in the phytochemicals. That's what I would utilize if I'm, answering many of my research questions. I know those secondary metabolites vary a lot with environmental practices, with climate change. So they're very vulnerable to shifts in processing. So that's something that I would be really interested in looking at. We know other compounds in food are not as sensitive to shifts in climate change, right? So it really depends, I think, like what the research question is for being more cost effective in the future. So right now, I would say that we have a big investment just to really map out everything. And this is really a foundational resource that with this information, then to really allow others in this public database to say, okay, what in food is important? What are we seeing that's unique in a specific food or that's prevalent, to really do further research to answer that question.
I have a follow-up question to that, which is, when I love the circle diagram where, Steve, you were showing the different compounds and what foods have high levels of those. And I just wondered if there has already been any effort toward a compilation of evidence for each compound's known function, like whether it's aromatics and flavor or pest resistance or related to cancer risk, that's, either known or suspected. Because what you just said is like, well, we know this compound has to do with something. Has that been compiled as in terms of what is known already that it could be added to by the centers of excellence?
So I'm going to start and I'm going to pass it to Chimay because this is really in his domain. But that is not compiled. It is it's transitioning from a conceptual activity to reality here as we enter this year. So there's a lot of existing knowledge that can be brought together with these data, not only in terms of chemical knowledge, but functional knowledge, all sorts of things. And the idea is to pursue, especially with new tools. I mean, we're seeing every day in the news, right? Like the kinds of capabilities that some of the new machine learning algorithms can bring together large data sets and begin to synthesize how these things can come together with our data is probably, for me, the most exciting part of this next year. Like bringing that together, it's going to be really powerful. And you can imagine, not just in terms of our ability to annotate things and tell people what is important about a study they do, but also to really drive the interfaces that we begin to think about developing for different audiences. A nutritionist is very different than a crop breeder, is very different than a biochemical researcher. So just thinking about all the ways we can bring that together is pretty cool. So, Chimay?
Yeah, I'll tag on to that just by saying that one of the things that we've been trying to really pay attention to is interoperability between the data that we're collecting and other folks that are doing that kind of work. So, for example, I showed you the ontology that the foods are being categorized in, and that ontology is we've adopted the Food On ontology, for foods. And so around kind of nutritional function, there's another ontology that's within the food on family called the compositional dietary nutrition ontology. And that's kind of a nutritionist way of organizing particular chemical compounds, but also with the concepts of connecting that to dietary function and to human health. I think that kind of work is being done with that ontology, and our strategy is essentially to do the pieces that we that the initiative is focused on in terms of cataloging the composition, making sure that that's captured in a way that is interoperable with other folks that are doing the nutritional function and human health function. So that's kind of the general way that we've been thinking about it. But I think a lot of that work is, you know, in progress, and we just want to make sure that we can kind of connect up with it.
Well, and Anna, your experience would be great if you can point us in good directions. That would be awesome.
Just add that we have demonstration projects that are beginning to tap into that in like smaller pieces. So not thinking about the scientific literature of all of and health attributes of all of the components in the database, but sort of looking at specific health attributes. So right now we have a grant where we're specifically looking at bioactive components for cardiovascular disease, and really seeing in our biochemical library, where does the literature suggest that there's already a wealth of information and evidence that these components somehow mitigate diet-related chronic disease in terms of cardiovascular health. So we do have small demonstration projects that are like taking parts of that into a deeper way.
Great. The next question is related to what we're talking about. It's where does the initiative hope that this further research will occur relating the diversity of compounds in foods to human health impacts and outcomes? So they're specifically asking about kind of how are we encouraging and enabling a further research to take place once the PTFI goes live and is public. So maybe I'll start with Selena, and then she can pass it around, talking about the vision we have for enabling the world's stakeholders to really do this further research and linking food composition to human health outcomes.
Yeah, so the data will be publicly available in order for it to be tapped into further, for there to be like big data analytics, for there to be linkages to other databases that are already looking at health attributes of different bioactive or biomolecules, bioactive components or biomolecules. So there, you know, with this publicly accessible data, we do hope folks are utilizing and looking at trends in the data. We also really are working with national labs to begin to adopt the tools, in addition to having methodologies for looking at things like phytochemicals in food. We're also developing the same tools for looking at these components in human serum, and want to further develop methodologies for looking at these components in human feces, so we can look at connections between food consumption, our dietary patterns, and other health outcomes, including for the gut microbiome. So really, in the future, wanting to support a series of demonstration projects with specific themes for human health and links to to soil health and planetary health. So funding a series of demonstration projects and also really working with national labs. Right now we have MOU with the USDA. We also have MOUs with other national labs around the world, including the Chinese Academy of Agricultural Sciences, other public health institutes like the Ethiopia Public Health Institute. So really working to partner with national labs around the world to collaborate in this type of work. And I would love to pass it to somebody else on the team to expand on that.
Maybe Gina.
Yeah, sure. I think Selena, you did a very good and comprehensive job, but I suppose I'll just kind of draw us back to the example from our Center of Excellence in Mexico, where, and just also draw on Selena's examples if it's a global project. And so the Center of Excellence in Mexico has prioritized foods, and they've also got a pretty good idea of the bioactive compounds that that already have associations to health. And now they're going to be looking at the abundance of those chemicals in the priority Mexican food list. And then they also want to start to work on biomarkers of intake of those foods. So I think it's kind of, a step-by-step process as we explore more and learn more about these bioactive compounds, and then learn more about where do we see the biomarkers of dietary intake through, as Selena already said, blood, serum, feces. I know there's also lots of excitement to explore how these interact with the gut microbiome, for example. So again, it's really a global project, and we're looking to find some very interesting examples from researchers around the world on these topics.
Great, thank you, Gina. I think that at this point, what we're going to do is we're going to invite all of you who have time to stay on to join us in a more open forum for discussion where we can see each other's faces and it's not so structured and moderated. You'll see in the chat a link, a Zoom link to join. Now the trick is you have to join the second Zoom meeting before you exit this meeting, or else it will be very difficult to find that discussion forum link. So click on the link if you can join us, and you'll exit this link, and we look forward to discussing your specific questions with you in more detail. Thank you.
Yep, ladies and gentlemen, go ahead and click that link and it will send you out of this webinar. See you on the other side. Thank you.